This is going to be a lesson about two special triangles that have really simple trig ratios. In order to talk about these special triangles, we're going to have to say something about the angles of any triangle. So to begin with, let's go ahead and draw on some random triangle. Now that we've drawn on this random triangle, we'd like to see if there's anything we can say about these three angles. If I rotate this triangle 180 degrees, there's actually something really interesting that we can say about it. Now if we look at this really carefully, we notice that the angles A, B, and C just add up to the angle of a semicircle, and we know that that is just the same thing as pi radians, or 180 degrees. Now just to clarify, if we knew the values of angles A and B, then we can use this to figure out what this last angle should be. Since 80 plus 70 is just 150, then we know that this angle over here just has to be 30. So this is actually a condition on what it means to be a triangle. If you have three angles and they don't add to 180 degrees, then you cannot use them to build a triangle. Now given this information, we're actually ready to talk about these two special triangles, which I can do on a new page. Now the first of these two triangles is called the right isosceles triangle. Now an isosceles triangle is just a triangle where two of the sides are exactly equal to each other. I can go ahead and draw the right isosceles triangle below the unit circle. Since this triangle lies on the unit circle, its hypotenuse must be 1. And because it's an isosceles triangle, its two sides must be equal. Now because the x-axis and y-axis are perpendicular to each other, then this angle over here must be a right angle. Now because this is a right angle, we can use Pythagoras Theorem to figure out what the value of a should be. We know that a squared plus a squared should be equal to 1 squared. Now of course, a squared plus a squared is just 2a squared, and 1 squared is just 1. Now we can divide both sides by 2, and now we can take the square root of both sides to show that a must just be 1 on root 2. So I'll go ahead and make that replacement and get rid of this working out. Now because this triangle is symmetrical, we can say that this side and this side must just be equal to each other, so we can go ahead and figure out what they're equal to as well. Now as we said, the angle sum of a triangle has to be 180 degrees. Since we already know that this is 90 degrees, we know that a plus 90 is 180. We can subtract 90 from both sides, and then realize a plus a is just 2a. If we divide by 2, we realize that a is just 45 degrees. We can go ahead and replace this on the diagram too, and get rid of this working out as well. Now because this 1 on root 2 is just the x-coordinate of this unit circle, then we can immediately say that cos 45 is just 1 on root 2. Now similarly, since we know that the y-coordinate is just the sine of 45 degrees, then we know 1 on root 2 is just the sine of 45 degrees as well. Now since the tan of 45 degrees is just going to be the sine divided by the cosine, we know that 1 over root 2 divided by 1 over root 2 is just going to be 1. So we can just write this fact on our list as well. Now this completes our discussion on the right isosceles triangle, so next we're going to talk about the half equilateral triangle. To do this, I'm going to go ahead and inscribe an equilateral triangle below the unit circle. An equilateral triangle is just a triangle where all the sides have an equal length. Now since we're calling this a half equilateral triangle, I'm going to go ahead and rub out half of the equilateral triangle, so we're left with half of an equilateral triangle. Now again, since we know that this lies on the unit circle, we know that its hypotenuse must again be 1. And this time, since it's an equilateral triangle, its base must also be 1 as well, and that means the distance from here to here must just be half. Now again, since we know that this line and this line are just parallel to the x and y axis respectively, we know that this angle over here must be a right angle. And because it is a right angle, we can go ahead and find out what this side is equal to by using the Pythagoras Theorem. Again, this time we know that half squared plus a squared is equal to 1. Now half times half is just the same thing as 1/4, and 1 squared is just the same thing as 1, so we can replace those. Now if we subtract 1/4 from both sides, we get that a squared is just the same thing as 3 on 4. If we square root both sides, we notice that a is just the same thing as root 3 on 2. Now to find these two angles, it's going to make sense to look at the outer equilateral triangle. So let's go ahead and label these three angles A. Now we know that a plus a on this outermost triangle is just going to have to equal 180 degrees, so we can go ahead and write that. We also know that a plus a is 3a. And that means if we divide both sides by 3, we just get the fact that a is just the same thing as 60 degrees. Now since this is just half of an equilateral triangle, then we know that this angle over here must just be half of a, so it must just be 30 degrees. We can go ahead and write this information directly on the triangle. Now just like we did before, we know that the x-coordinate on the unit circle is just the same thing as cosine, so the cosine of 60 is 1/2. Now similarly, the sine is just the same thing as the y-coordinate, so the sine of 60 is just root 3 on 2. The tan of 60 degrees is just the gradient at 60 degrees, so we can go ahead and divide root 3 on 2 by 1 on 2. Now since division is just the same thing as multiplication by the reciprocal, we can go ahead and flip this second term. Now since these 2's crossed out, we can just see that the tan of 60 degrees is just the same thing as root 3. Now to deal with this 30-degree angle, we can just go ahead and use SOHCAHTOA, which we introduced in an earlier lesson. Now to get the cosine of 30 degrees, we just get the adjacent and divide it by the hypotenuse to get root 3 on 2. Now to get the sine of theta, we just divide the opposite by the hypotenuse, so we just get 1 on 2. Now finally, to get the tan of 30 degrees, we just divide the opposite by the adjacent, which gives us 1 on 2 divided by root 3 on 2. Now again, remember division is just the same thing as multiplication by the reciprocal, so we can go ahead and flip this second term and turn it into a multiplication. This time, after crossing off the 2's, we're left with 1 on root 3, which we can go ahead and write. Now you're very likely to see these ratios so many times that most of you will commit these to memory. But you don't really ever have to commit them to memory because you can always just draw these triangles and work out what the values are. Now as a final remark, I just want you to remember that 45 degrees is just a quarter of a semicircle, which means that it's just the same thing as pi on 4 radians. Now 60 degrees is just the same thing as a third of a semicircle, which means that it's just pi on 3 radians. Now 30 degrees is just the same thing as 1/6 of a semicircle, so 30 degrees is just the same thing as pi on 6 radians. Now because these angles are just the same, we can go ahead and rewrite any of these ratios in terms of radians. I'll just show you with this one just to demonstrate. So that means if you're working in radians, you can just say that sine pi on 3 is the same thing as root 3 on 2 as well. Now it's important that you get familiar with all of these ratios because you're going to see them a whole lot. And with that, we've actually completed our discussion on these two special triangles.